Right, afternoon. Today we're going to do paper 1 from last year's Edexcel papers. So let's get going. First question. We've got a point at 6 minus 4 lies on some curve. Find the point to which P is mapped when the curve of the equation is transformed with this new equations. So the first one, we're going to move left by 2. So instead of being 6 minus 4, it's going to be 4 minus 4. So that's 6 being moved left by 2. This means inverse. Inverse is you reflect in the line y equals x. So our coordinates effectively swap place. We should have minus 4 and 6. And this should make sense when you think about what we want from the inverse. We would put the output in there, and it's going to give us the input. So everything should be the other way around. For this one, let's think what's going on. F of x was minus 4. When we took the modulus of that, we get positive 4. Doubling that is 8, and then taking away 3, it gives us a 5. So our y coordinate is 5, and our x coordinate hasn't changed. So it should be just 6 still. So that nice and easy 4 marks for that one. Everything looks good there. So we'll keep going. Number 2, circularize this equation. So x plus 3 squared, y minus 4 squared is 24. State the coordinates of the center. So this works similar to the transformations. When we're inside a bracket, it kind of works the wrong way around. So this is moved left by 3 and up by 4. So the coordinates of the center are going to be minus 3, left by 3, and then up by 4 gives us a positive 4. So that looks good. Find the radius of C. Give your answer as a fully simplified surd. So the radius here, well, 24 is the radius squared. So if we know that r squared is 24, then that tells us that the radius is 24. And simplifying that surd, think 24 is 4 times 6. Square it in that 4 gives us 2. So it should be 2 and then root 6. All looks good. Now part B, determine, given a reason, whether or not the origin lies inside the circle. So to test that, we want to think about inside the circle is going to mean that x plus 3 squared plus y minus 4 squared is less than 24. Well, if we go and put in the origin, i.e. 0, 0, what we end up with is that 3 squared plus 4 squared equals 25, and that's bigger than 24. So therefore, the origin is outside the circle. So yeah, this one, this means inside. What we're really thinking about, this measurement is a distance. How far away are you from the center? So it's just like this is then the square of the distance away from it. Think of magnitude, same sort of idea. So we're showing the distance away the origin was 25. So that's further than the 24. Well, the square of the distance was 25, which is further than the square of the 24, square of the radius we were allowed. So we'll keep going. Number 3, we have an arithmetic sequence. So there's a common difference between them. We've got the first 3 terms, and we'll find the value of k. So first 3 terms, what that's going to tell us is the difference, so 10 take away 6k, is the same between the first and second and the second and third. So the 10 take away 6k will be the same as 2k take away 10. So if we add 10 to both sides and add 6 to both sides, or 6k to both sides, we'll have 8k is 20. And therefore, we get that k is going to equal 5 over 2. That all looks good. It's probably worth just getting the numbers straight away. You'll most likely need them anyway, the next bit. But yeah, probably worth looking in there. At least for the first one. So down here, we need to find the value of the sum of the first 50. So what we're going to need for that is the first term. So 6k when k is 5 over 2. So half of 6 is 3, times the 5 is 15. This is a 10. So what we have, the difference in it is negative 5. So we've got A is 15, and the D is negative 5. That A looks very D-ish. A. There we go. So the sum of the first 50, using that formula, we need to have 50 over 2 times by twice the first term. So 2 times 15 is 30, plus n minus 1, so 49, times by the common difference of that minus 5. So let's stick that all in the calculator. So we've got that 25 at the front of the brackets of 30. Take away 49 times 5 gives us negative 5,375. So that looks good. Like I said, I will double check these at the end just to make sure everything's fine. But this all looks good to me. Like it should be negative. Our common difference is negative. So we're going to go like 5, 10, So 15, 10, 5, 0, minus 5. And then get smaller and, well, bigger in magnitude, but negative. So smaller numbers are going to give us a negative answer. So that looks good. Let's go to number 4. We have some cubic, and we're told that it has a root at -4. So let's write it in this form. Well, when we have a root at -4, we can take x plus 4 as this. So a is going to be 4 in this case. So if we do that, x plus 4, the way I do these, you can either do long division, like that will work, but it's long. It's in the name. So let's do a shorter way that isn't even short division. But we can think about, where does this term come from? It must come from the x and the x squared term in here, in this quadratic. So we have x there times by what gives us 2x cubed. We need to have 2x squared. Same logic applies to the constant, like where's this 16 coming from? It's 4 times something, and that something must be 4. And then in the middle, it's a bit more complicated. We can think about, how many x squareds do we have? Well, if we combine these two together, that gives us 8x squared. We need to end up with 3. So we know that these two bits must take away 5x squared to give us the total of the 3. Every other combination, like think about expanding the brackets here, wouldn't give you an x squared term. You get 2 of each term apart from the first and last, which you get 1 of. So doing that, we know we need minus 5x squared. This is just x, so we need minus 5x to go in there. And then that's our full quadratic. That all looks good to me. Prove that minus 4 is the only real root. So let's look at the discriminant of q. So the discriminant is b squared minus 4ac. So b squared 25, take away 4 times the a of 2 times the c of 4. What is that up to? Looking at this, we have that 16 times by 2 is 32. So 25, take the 32, is negative 7. That is a negative number. So therefore less than 0. So that tells us that we have no real roots. So therefore negative 4 is only real root of the entire cubic that we had, so f of x that we were given. So it's no real root of q, I suppose. Yep, that looks good to me. So yeah, this was the only root. This one had no roots, so this one must be the only root. Let's keep going to number 5. Express this horrible thing as an integral. So that's kind of the definition of an integral. So it's only 1 mark, so there's not really much to do. Just actually, where you see this kind of limit with the sum after it, that becomes the integral symbol effectively. Starting from 1.44, going to 2.89. So 1.44 at the bottom limit, 2.89 as the upper limit. The function is the same. We've got this 2 over root x. So we'll have the same 2 over the square root of x. And then you have the dx there. So dx on the end as well. That's all good. Now I'll show that equals to some number. So it's just to like do the integral, basically, to solve this thing. So let's do that. I'm going to rewrite this though as it is 2 times by x to the power of negative a half. So doing the actual integral now, we're going to have raise that power by 1, x to the half, divide 2 by a half. So divide by half, same as times by 2. So we'll have a 4 out there. And then we have those limits of 2.89 over 1.44. This would be nice to whack it in a calculator, but no calculations are allowed. So let's actually walk through how we would solve this one. It's not so nice, do you know what I mean, looking at it, decimals and square roots and things, but if you know your square numbers, 289 is 17 squared, and 144 is 12 squared. So what we can do, if we go and write this in there, take that 4 out the front, we're going to have the square root of 289. But I'm going to rewrite that as 289 over 100, and then both of them square rooted. And then doing the exact same thing for the 144. And remembering that what we have over here is going to be 17, and this is 10. This is going to be 12, and this is going to be 10. So we effectively have, I'll take the 10th out the front. So 4 over 10, lots of 17, take away 12. So this is going to give us 5 times 4 on the top is 20. 12 over 10 is 2. It's a very nice number. That looks good to me. Yeah, all looks good to me. So let's keep going. Number 6, we're monitoring flight of seabirds after they leave their nests on a cliff. The height is going to be given by this one, where t is time. So when you look at this, first, like, spot a few things. There's no exponentials, but there's powers of t, but there's no like e to the power of t. So when we look at this, the power's going to be doing most of the work. This at 0, the whole term will be 0. So the initial height is always going to be a in this case. If this was like e to the t, what we'd have is that e to the t when t is 0 is equal to 1. So our initial height would be a minus b in this case. So that's one thing to always kind of spot out for these ones. And here it's just t. There's no, like, say, t minus 1 to the power of 1.5. In that case, what you'd see is there's like, it's centered around 1. So you'd have maybe like an increase then decrease. In this case, we're only going to get a decrease. It's basically t to 1.5 is a fully increasing function if you're like in that quadrant. So when time is positive, which it always is here, this is always going to be positive. So this whole thing is always negative. So we're always going to be less than our initial value of a. So that's good. What's the question want us to do now? We are 17.6 above after 4 seconds, 11.9 above after 9 seconds. Complete the model, so find A and B. So these two simultaneous equations, let's plug them both in. When the height is 17.6, what we get is that A, take away B, and T, if you think T to 1.5, that's the same as 3 over 2. So we need to square root then cube. So 2 square root, 4 square root is 2. Cube that is 8. So we actually have 8b. Similar sort of way then, the 11.9 is going to be a take away 27b. 9 goes to 3, which goes to 27. I will just write these other way around. It's a bit easier to do the subtraction when you've got the bigger numbers on the top. No, what am I saying? Don't do that. This is already the right way around. So doing that, what does that give us? 0.1 to go to 12, another 5.6, so 5.7, and here that's going to be 19. So that tells me that B is going to be 0.3 or 3/10. And then we can go and plug this back in there. I'll actually plug it into this one, I think, maybe. Will that work? No, I'll do this one, probably easier. So doing that, A is equal to 8 times B, so 2.4 plus the 17.6, which gives us 20. So we have B, we have A. And here it's asked for the full model, so I would still write down the full model. I wouldn't just leave it as like, I know we've done all the work, but they asked for the complete equation. So just still make sure you actually put with the numbers in it. I'd still make sure you write down the actual full equation at the end, just to make sure. They probably won't mark it down, but you never know. So that all looks good to me. For part B then, the height of the bird's nest, well, it starts at the nest. So that's just the initial time. You see the marks in 1 mark. So I think that's just going to be the A value, the 20 we said. Like I said earlier, like A is going to be the initial height in this case. It's always either just A or A plus B or A minus B, depending on the sign in the middle. So that's good. Limitation on the value of t. So in these ones, think like what would not make sense, or have they limited it somehow anyway? So we're saying the height has to be positive. That makes sense. Birds can't dig. birds can't dig through the ground like moles or something. So let's take this equation and make h positive. So we have 20 minus the 3/10 of t to the 1.5. I'm actually going to write 1.5 there as 3 over 2. That needs to be positive. So let's rearrange this. We can add the 3/10 stuff to the other side. So that is all going to be less than 20. Times by 10 divided by 3 gives us t to the 3 over 2 is less than, times by 10 is 200, divided by 3 on the bottom there. So let's just do the inverse power of that. So it's going to be like t is equal to 200 over 3 to the power of 2/3. That is effectively the time that we, well, not equal to, that should be the time that we hit the ground at. So are we allowed to be on the ground? Probably. Does that just count as landing? Depends where you have like measured the height of the bird from. If you measure it from the top of their head, then no, because then their body would be in the ground. But if you measured it from the bottom of their feet, yes. So in this case, I'll include the 0. Like, we're going to include that time just in case. It's one of those, like, they haven't really specified, so I don't think you lose marks either way. Should be fine. And they've said here that h is allowed to be 0, so I think that we should include it. Yeah, that hopefully is all good. So let's keep going. I will just circle our answer for the part B though, and for this down here as well. So number 7, got some quartic in here. Blah 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 blah. Turning point at -1, 0, and 5, 0. Cross the axis here at -75, and a turning point at 2. Find the set of values for when the gradient is positive. So we can see that's like this section and this section. So it's whenever x is less than -1 or between 2 and 5. You can see here we do include when it's flat, so that does include all of those numbers. They want our answer though in set notation. So let's do that. So set notation, you need to tell them what type of number it is, and then what conditions do we have for the number. So the first thing, our numbers are real numbers here. We're not dealing with complex numbers or just integers, something like that. So we will have x is going to be a real number. And the first condition, it could be less than -1 or less than or equal to -1. And that's going to be one set of the numbers. So it's all of the numbers like from -1 that way. Then we also want between these two. But we can be in either group. So we're going to take a union of that set with another union, or with another set, sorry, where we're between the 2 and the 5. In the real world, you could just put a union, like you could cross all of this stuff out. This is how we were taught to do it at uni. It was fine. I don't know why the exam seemed to want it written as 2 sets. Either way, it's not too much extra writing, do you know what I mean? So just think like each inequality basically gets its own set, and then you're going to combine those sets together. You're never going to combine inequalities originally. So that's good. That looks like the correct stuff for that mark. To get the numbers all right. Yeah, -1. Part B then. Find the equation of C. So it's a quartic, so we should have 4 brackets. But we have these repeated roots. So just like in a quadratic, where you have a repeated root gets a square bracket, same thing happens here. So it's going to be, say, x plus 1 squared and x minus 5 squared. But we don't know if that's been scaled up or down. So you can imagine we could have like this sort of graph where it's the same stuff, but it's just been flattened. Or you could stretch out even more, do you mean have one that does this sort of stuff, like this sort of stuff. So we will just put some scale factor at the front. How do we solve that then? Let's plug in 0, make sure we get -75. So if we do that, plug in a 0 there is 1, so 1 squared is 1. Plug in there is -5, 5 squared is 25. So we have 25 alpha on that side. So 25 alpha should be the -75. So therefore alpha is going to be -3. So that's good. We can then rewrite the entire thing back out again. I will put it down here by the answer though. So y is -3 x plus 1 squared and x minus 5 squared. For part C now then, the new curve has been moved up some amount or down. Given that it intersects the x-axis at 4 places, find the possible range of values of k. So we can either think about moving the whole thing up, or we could think instead about like moving the axis down. It's like how far can we move it down? So we can't move it up. If I move it up, it doesn't hit it at all. So we definitely can't move it up. How far down can we go? Well, this is all fine until we get to this point. So you can see like we've got 2 roots in the middle, and then they combine to make 1 and then 0. So it's that cutoff point that we don't want. So that's kind of the lowest we can have there, the axis, or there. So we just want to find really how far away is this point. We know that this is going to be, but the top line we've moved at 0. Here we will have moved it however far that length is. So let's plug in 2 to the function, see what number we get. Where is the function? Down here. Was it called f of x? It was f of x. I will write it as f of x then. So f of 2, putting that in there. We have the -3 at the front. 2, that makes a 3. So we're going to have 3 squared there. So -3 times 3 squared. And in there, we're going to have -3. But when we square that, it's just same as 3 squared, isn't it? So altogether, we have -3 to the 5, which is -243. So that tells us that was kind of the bottom point here. How far could we move that up is 243. We needed to have exactly 4 places. So 3s are not allowed. So we do need to move it a bit. We couldn't leave it where it was because there we only have 2. But if we move it a little bit, we do get 4 immediately. So k must be bigger than 0 and less than 243. Just make sure that's all the right way around because we're moving up. K, yeah. K should be positive to move up. It is positive there. Me move the graph up to that line. It's all good. Lovely, jubbly. Let's keep going. Awesome proof stuff. So they're proving that the square of any number can be written in the form of 5n, or 5n plus 1, or plus or minus 1. So that means that it's a multiple of 5 or 1 either side. That's what they're saying. So you think like when the remainder of it would always either be 0 or 1 when you divide by 5. So they start the proof, blah, 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 blah. Find the error. Okay. These are always quite difficult to do. It's just a case of, it's sometimes easier to do it from scratch and see what you do differently, especially like part B down here. If you read it, it's actually just to complete the proof. So sometimes we could just like do the whole proof from scratch and you'd find this algebraic error you couldn't see as you go through. As we do look though, so m is 5k, we're going to square it, 5k squared, that looks fine, 25k squared, that's fine as splitting the 5 up. They've done that just so that it's 5 times something, do you know what I mean? Don't care what this something is, just need to be 5 times something. So that's good, 5n, and then yeah, n is that stuff. Same thing here then, k plus 1 now, square those brackets, no, that's fine, yeah, k plus 1, that's fine. Take the 5 out with a 1 left over, 5n plus 1, n is that stuff, that's good. So it must be in here somewhere, you'd assume. 2, yeah, this shouldn't be 10. 1, if you did FOIL, the O would be 10k, and the I would be 10k. So this should be 20k. So I would just write down like 5k plus 2 squared is equal to 25k squared plus 20k plus 4. So this is, yeah, not 10k. That looks good. Part B then, to actually do the proof. So think of the numbers they've tried. They're going to go through and try all the different multiples. Well, not multiples of 5, but all the different numbers, possible remainders of 5. Either you're a multiple of 5 or your remainder is 1, 2, 3, or 4. If you get remainder 5, you're just the next multiple of 5. So they've done 0, 1, and 2. We need to do 3 and 4 then. You could be a bit sneaky and just do like plus and minus. It's quite nice. But we will just do minus 1 and minus 2. So if we basically just copy it word for word actually. So let m is equal to 5k minus 1. And then we're going to consider m squared equal to 5k minus 1 squared. So expanding those brackets, we get the 25k squared minus 10k plus 1. And that is 5k, or 5 times something. That something being 5k squared minus 2k. We still have that plus 1 on the end. So we can write that that's equal to 5n plus 1, where the n is that thing inside the bracket, the 5k squared minus 2k. And now very similar then, we're going to let m equal to 5k minus 2 and consider m squared, which is the same as 5k minus 2 squared, which is the same as 25k squared minus 20k plus 1, plus 4, sorry. So the proof is very long-winded. It's a case of just having to write down every step. You can't really skip any. I've just been a little bit careful about how we're going to do it. So this is where it's different. We have the 4 here. See what they did above? We've got that 4 as well. So we've really split that into like plus 5 minus 1. And then the 5 gets factorized inside the bracket with this plus 1. And then you're left with that minus 1 on the outside. So same thing happens here. This plus 4 is really plus 5 minus 1. So that 5 gets factorized, as in there's 1 5 there. And we still have the minus 1 left over. So that is 5n minus 1, where n is equal to all that stuff in the bracket again. 5k squared minus 4k plus 1. And now then the last little line. So we've now looked at all cases. This is proof by exhaustion. We've looked at all the possible remainders when something's divided by 5. So we've looked at all different values of m, basically. All different cases that m could be. So now we've done that, we can write down that we do have, like, the proof is true, basically. How to put that in a sentence then? So therefore the given statement. So given statement, you can write the statement again if you want to, is true for all possible cases, all possible remainders of 5, and therefore is true for all, we've done k, so we're doing m, sorry. So for all m's which are integer numbers. Looking at it, I don't think we actually really cared about the fact that it was a positive whole number. Like if k was negative, I don't think it would actually change anything about what we've done at all. But we did only actually like start with it being a positive whole number, not a negative. Like no, like negative one's not allowed there. But it looks like it would be exactly the same proof. You just put that instead. But yeah, that's it. So it's exhaustion by splitting up all the different integers into different kind of remainders of 5, looking at all of those cases individually, showing that they all work. So therefore, it works for every single possible number. So that's good. Let's keep going. Well, one thing actually to note, it says number, not integer. So we should be able to write like 1.5 squared is not, it's just that's what 2.25. It is equal to that, which is not like a multiple of 5. Do you know what I mean? Not an integer multiple of 5. So really, this is wrong. It's not true. They should have written integer up there. But I think you'd get the marks. I think if you did that, you should get the marks because that is correct. But it's risky. Do take the risk if you want to take it. But yeah, I wouldn't be doing that. Maybe do both for me. Do the real one and do that as well. So next one, number 9. We've got a racing car driving on a straight road. We've got the speed it travels. Starts on rest, driven for t seconds before stopping. We've got the speed of it down here. T is the time it takes to move. Find the value of the time it takes to stop, when it stops, basically. So when does this equal to 0? So if we factorize things out, we can factorize a t out. And then we'll have a 15 minus e to the t on 5, that 0.2t, equal to 0. So you can see t could be 0. That's just its starting point. If we look then at the bracket, what we have is that e to the t on 5 is equal to 15. So t on 5 is the natural log of 15. So t should be 5 log 15. This should be capital T, really. Let's put that in there. I think that's the same on all of these, but you won't lose any marks for that. One decimal place for, what does it say? That's always something worth looking for, do you know what I mean? So 5 log 5 is 8.0. 8.0? 8.0. That looks good to me. When we look about B then, find the maximum, show the maximum speed occurs when this happens. So maximum speed, we need to differentiate. So let's find dv dt. Doing that for the first term, 15t becomes just a 15. For the next term though, we need to use the product rule because we have t and we have e to the 0.2t. So first if we differentiate t, we get 1. And then we just times it by the e to the t on 5. And when we differentiate the e to the t on 5, that t on 5 comes down. So we're going to have like a fifth of t. I'm going to rephrase what I said there. So it's not t on 5 that comes down, but just a fifth comes down. The differential of the t on 5. So just a fifth comes down, combines with the t that was already there to give us then that t on 5, which is then still multiplied by e, the t on 5. When we find the maximum, we want this equal to 0. But before I do that, I'm going to just factorize out the e to the t on 5. So we have 1 minus t on 5 lots of that. And I will take a fifth from that as well, just to make it a little bit easier to work with. So e to the t on 5, all over 5, and it's 5, 5 plus t in there. So that looks good. We want this equal to 0. So this, you can't solve this. You don't know ways to solve this in A level, where we have both t in exponential form, or like in an exponential, and just in a like parity. So yeah, you don't know how to deal with that really, but we can do iteration stuff. And you can see this one, we do have like t on both sides of it, but we can see we end up with a log. So we don't want to rearrange for this t. We currently want the t that's inside the eland, and then we need to rip it out of eland and put it into, well, put the other stuff into logland. So let's rearrange for e, basically. What we can do is times by 5 everywhere. So we're going to have 75 is equal to all our e stuff, so e to the t on 5. And I could write this bracket here, like this bracket just go here, but I can just straight away put it down there. So 5 plus t. And now if I take logs of both sides, I'll have t over 5. But again, I can just times by 5 immediately. And then I'll have the natural log of that bracket, of that fraction. So 75 over the 5 plus t. So that's not too bad, taking logs and then times it by the 5. And we do get exactly what they want. And the next one is iteration, and hopefully no issues doing that. I will do it, but it's just a case of we take this and put it in the calculator. So what I'm going to do is press, we're told that the first one is 8. So let's press 8. And then I'm going to type this out, but this t will be answer. So 5 log of 75 over 5 plus answer. And then we started, the first one was 1. Be careful because sometimes the first one is 0. So when we press answer for equal to the first time, that will give us the second one, t2. So we need to press answer twice to get the third one, which is going to be 8.478. And then for the part 2, find a repeated iteration, we're just going to spam equals until it stops changing number. This can take a while sometimes. Depends obviously how accurate your calculator is, but it should not take a huge amount of time, but yeah, a bit longer than you kind of want it to take. Is that good? Yeah, that's good. So what do we have? Lots of decimals. 8.554 02341. No, 401. Lovely. So they're all the bits we want for the answers. Got that circled already. That looks good to me. Yeah, lovely. Let's keep going. Number 10. Some vectors. So we want to find P to R. So how do we get from P to R? We can go from P to Q and then Q to R. So let's do that. We just need to add them up. So how many I's do we have? We have 8 of them. How many J's? We've got 8 and we've got nothing in there. Be careful, there's like, yeah, it's not to like just to go adding kind of like column by column, but this should really be placed like under here, do you mean? So 8 for the J's, and the K's, we've got a -2 and a +6, gives me a 4. I don't want to write this as IJs and Ks, just do that, like, it's better. IJs and Ks is just messy. This is good, this is the answer. It's probably worth writing down that this is like, you can factorize it, 4 lots of 221, just in case you need to do stuff with parallel later on. It's a very quick thing to do. Show that the triangle is both right angled and isosceles. Lots of ways to do that. You can do some stuff in further maths, but I won't do that obviously. But another way, isosceles has 2 sides of equal length, right angled. They will work with Pythagoras. So let's do that. What we can see lengthwise, I'm going to guess that this PR that we've made is going to be the longer one. So let's find the length for the shorter ones, and then find the length. We need to find the length for all of them anyway, so let's do that first. So the length from P to Q is, well, I'm going to factorize that as well. That's the same as having a 2 outside and then 1, 4, 1. The reason I do that is just so the Pythagoras is a bit easier. So it's 2 times the square of all of this stuff added up, like the square root of Pythagoras and all that. So 1 squared plus 1 squared is 2 squared, is 2, plus 16 is going to give us 18. So this is 2 root 18. And then simplifying the surds there, we get 9 times 2 in there. So it's going to be 2 times root 9, which is 3, so 6, times with a root 2 is left over. Let's do Q to R. And it will probably actually be worth writing this down as just a square root. It is the square root of 72. Q to R then, 6 and 6. So we can factor that very easily. That's going to be 6 lots of 101. So that's 6 lots of 1 squared plus 1 squared is 2, root 2. And again, that is root 72. Last one then is P to R. Length of that. So I've already got the 4 at the front. And then I will get 4 plus 4 is 8, plus 1 is 9. Square that is 3. So this is 12, which is the square of 144. So that's good. What I've shown then, I've got 2 facts now. The length of PQ is the same as the length of QR. And that when we do Pythagoras with like PQ and QR. They fit Pythagoras nicely with PR. So yeah, we've got this triangle where PR is a long side and QR is a little one. These have a length of 2 root 6, 2 root 6, and this has a length of 12. Don't know about the angle, do you know what I mean? It might be some weird angle. Do you know what I mean? It could be like, yeah, on a tilt or something, but you could draw it accurately if we had all the stuff, but it's only 3D, so you can't really draw it so accurately. But yeah, that's all fitting, all relative to each other quite nicely. Let's keep going. Actually, I would probably write some words here. This is going to be like isosceles, and this means that it's right angles, just in case. Yeah, number 11 then. The value of a car is multiplied by this equation. Given that the initial value of the car was 20k and the value of the car was 12 grand when it was 2.5 years old, find the complete equation for the model. When you see a model like this, it's pretty much always what you're doing. So let's plug the values in. Initial value was 20. So this is the opposite. Remember earlier we had that t to 1.5, and when we plugged it in, it was just like the number that was here was the initial. But here we've got e to the parity. So when we plug in the initial time of 0, this becomes like e to the 0, which is 1. So 1500 plus a will equal 20,000. So 1500 plus a equals 20,000. So we know a is going to be 18,500 pounds. That's good. The value of the car was 12 grand when it was 2.5 years old. So this will give us the K value up there, the kind of decay rate of the price, depreciation rate you could call it. So let's plug it in. We'll have the 12,000 is equal to the 1500 plus the 18,500 times by e to the minus, and 2.5 is 5 over 2. So I'll do 5 over 2 lots of k. Lots of zeros here. I'm going to like divide it by 100 just to make it a little bit nicer to work with. So 120, take 15 is 105. Let's divide that by 185. Then we're left with this stuff, so we need to take logs of that. And then we need to divide that by 5 over 2. So times it by 2/5, negative of that. So that is our value for k. K here, like we're going to do negative stuff with it. And right now this looks like a negative number because of this, but the fraction in there is smaller than 1. And when you take the natural log of that, we're going to get a number that's less than 0. So this is actually a positive number. So I will just rewrite it as it's going to be 2/5 of the natural log of 185 over 105. So flipping that fraction over, and we can actually simplify that down a bit. 5s will go into it, 21 on the bottom and 37 on the top. So yeah, 37 over 21. So now this again looks like a positive number, which is what it is. It's not so important, but it's good like to keep it clear in your head that it is a positive number, not getting you confused later on, like thinking it might like, so it's got a negative in there and a negative in here, so it's going to be like a growth rate, do you know what I mean? But this is not, we're having a decay rate in this one. Part B then, we want bloody decimals again, so 3 sig figs, that's good. This will be something, some number, where's my calculator? So 0.4 log 37 on 21 is, I don't know why they make you do this, 0.227. That looks good to me. Let's move this over here then. So that's the answer, isn't it? Yeah, that looks good. Let's look for, I suppose A is the answer as well, isn't it? For part B then, yeah, let's find this growth rate or rate of change. So we need dv dt. And we have some exponential stuff. So the 15 is going to go. There's no t's or anything in there. What happens over here is the minus k will come at the front. So it's effectively going to be like minus ak e to the minus kt. I could write in the numbers for this. And I will do obviously in the last step, but right now it's going to be pretty horrendous. I don't want to use this. That's an approximation. Don't want that ever. Always want the real one. But that's not so nice to be working with. I mean, you can see it doesn't appear in here. So most likely it will cancel out. So what we can do actually, is to see that we don't have time in there, but we do have it down here. So we want to remove this from our equation. How can we do that? By using the original one. So if we rearrange this for e to the minus kt, or even a, don't you need to divide the a. So yeah, we can have a e to the minus kt, which is just v minus 1500. And that looks very nice. Very nice that things start appearing. That's always a good sign. If bits that you rearrange to are part of the answer, that's always a good sign. So let's do that. We can replace most of the bits of the a and the e to the minus kt with this thing. So this is effectively equal to minus k times by v to the minus, or v take away 1500. Oh, and that's it. That's all we need to do. Okay, nice. Lovely. That was a nice easy 3 marks. State the limitation of this model. Looking at it, e to the minus kt does this. It goes down and then it goes to 0. But if we're adding that to something, it's not going to go to 0. It's just going to go to what you add it to. So it's never going to go below 1500. So this car is just always worth at least £1,500, which is not going to be true. How I would write that down is thinking we have e to the minus kt. That's always positive. Or when t is positive, it's going to imply that. Can t be equal to 0? Maybe, but it doesn't matter. So that's true. And now then we can build this up. So if we times that by times that by whatever a was. Again, not writing in the number for a, it doesn't matter here because it's just going to keep being positive is the main point. And then if we add on the 1500, we will have 1500 on the right hand side as well. And that is exactly the value of the car at the time. So the value of the car is always going to be above 1500. I don't know if you need to do this kind of derivation. If you understand how to just write that down, I think that would be fine. It's only 1 mark. But it's always good to kind of like understand why it's true, just in case there's a more complicated equation that you're given to work with. That is good. Let's keep going to number 12, wherever it is. We've got something horrible. We've got this curve with a straight line. Where's that straight line? Over here. That's 2x minus 10, blah, blah, blah. That's just because it's going to be having these bits. So verify that they intersect where x is 6. Okay. Where to do that, they have the same x coordinate of 6. They have the same y coordinate. If they do, they intersect. So let's look at the curve to begin with. So y will equal 15 times 6 is going to be 90 on the top. Let's just put that straight away. On the bottom, 2x would be 12 plus 3 is 15. And then times by 3. So that's 45 on the bottom. So that's going to be 2. And when we look at the line, I'll always do a capital L for lines because lowercase l is just, yeah. For the line then, 2x is going to be 12 minus 10 gives us 2. So these are the same. Because they're the same, they intersect. Because we know that when they have x coordinate of 6, they have a y coordinate of 2. So they're both at 6, 2. So they're both there at the same time. They have intersected. Part B then. They also intersect at point Q, which is down here somewhere. So important to notice, like it could be one of these two. Like there's going to be 3 intersection points. Let's actually circle those. 1, 2, and 3. It's only negative 1 though. So that's what we need to look out for when we get that. We want to find it's a solution to this thing. Okay. So to find intersection points, we take the 2 curves and equate them. So we're going to have the 2x minus the 10 is equal to that 15x over 2x plus 3, x minus 3. And let's do some rearranging then. So these 2 brackets are going to end up like next to this one. But I don't want to kind of do that first. I will expand these first and then kind of move it. But I will just write it up here, do you know what I mean? So 2x minus 10 in that bracket. And then this bracket is going to be the expansion of this stuff, which has been kicked over there. So 2x squared. I'll get plus 3x minus 6x. So that's going to be minus 3x. And then a minus 9 for that 3 and minus 3. And this stuff will all equal 15x. Next part then I need to expand these brackets. This I do power by power, I think is the easiest way. So I'm going to go through and get, it's the same as I did the square brackets, do you know what I mean? Just because there's an extra term, same sort of idea. So the highest one's cube, 2 times 2 is going to be 4. Let's look at squares next then, so I can get them from there, which is going to be minus 6, and from there, which is minus 20, that's minus 26. And this is always looking good when they start to match the show that kind of destination. The x's then can come from there, that's minus 18 of them, and there, that's plus 30, so I've got 12 there. And the just constants, I'm going to get a 90. This equals 15x still. If I take away the 15x, I get exactly what we are after. So that 12 becomes a minus 3. And then we're good to go. I guess part C, yeah, part C is to find the thing. So above, we were told that they intersected like when x is 6. We're going to use that then to very similar. Remember earlier on we did this like wherever it was, factors in this thing, this quadratic into, no, cubic into a quadratic. Was it this? No. Wherever it was it really that long ago? Yeah, this thing. Exactly the same process. We know what the numbers are, and we're going to then go out and make a quadratic from it. So let's go back to where we were. This one. I'm going to take this to a new page though, because I haven't got enough space here. So let's copy this over, put it on this page, and our root was at 6. Was it positive 6? Yeah, positive 6. So one of our brackets will be x minus 6. And then we know in here we will have something that is a quadratic. How do we make this 4x cubed? It must be from this term and this one. So that will be 4x squared. Same idea. Where's this 90 come from? Minus 6 times something. Minus 15 in there. And then let's look at where this makes a minus 24x squared. So we need these to make minus 2. So minus 2, we've got a 1 over there, so we do need a minus 2x to go in the middle. Lovely jubbly, that looks good. Did we need to do anything else with that? Oh, yeah, okay, final. Okay, we need to factorize this as well. So let's factorize this. Is it nice? Maybe it's nice. Let's try. It's a bit too many options. 4 and 15 is 60. Square root of 60 isn't nice. Does it work nicely? 6 and 10. What else could we have? 9, no. 8, no. Does it not factorize nicely? I don't think it does. So in that case, we will do the quadratic formula. I don't have one of those calculators to do it, do you know what I mean? So the discriminant is going to be 4, take away 4 times by 4 times by negative 15, so we'll add that there. 16 times 15, 240 plus 4, 244. Yeah, that's not a square number, I don't think. Square root of 244 is something. 2 root 61. So effectively x is going to be minus b, so 2 over 2a, 8, plus or minus 1 over 2a, an eighth, of 2 root 61. So it's a quarter, well, 1 plus or minus root 61 on 4. So therefore q, the x corner of q, is going to be the lower one of that when we have the takeaway. Because I didn't put the plus minus in there. Lovely. That all looks good. This is one that I will double check. Do you know what I mean? It doesn't seem so lovely. So if I get a different answer when I check at the end, I will make sure that everything is fine. Or like I'll redo it. Do you know what I mean? So if I see immediately, I don't think so. Was that the right? This is correct. And like, this doesn't seem right. Do you know what I mean? When you get a number like this, it just doesn't seem like it's going to be so simple. Was the square 244 something? No. This is looking good. That is minus 24, minus 2. So let's check the single powers of x then. Does this work out correctly? So that would be 12x. And the other x's here would be minus 15x. Yeah, that is good. Maybe I've just done this factorizing wrong at the end. Yeah, I'll check on the calculator quick and then see if it's if it's fine. The number looks horrendous though. What do we get? 4x squared minus 2x minus 15 equals 0. No, it is. It is as horrendous as it looks. Yeah, I'll double check at the end as well to make sure, but that all looks fine to me. Nothing seems to be awry. So we'll keep going. See what we get for number 13. Just do some integration. So, few options here. You could probably do by part. You could probably do by parts. It's not gonna be so nice, but you could do partial fractions. I think that'd be very long-winded. I think the easiest, quickest way here is substitution. So if we make our u equal to 2x plus 1, notice it's not including the cube part. What we have is that du will equal to 2 dx, and the x will be u minus 1 over 2. Let's have a look at the limits. If we have x equal to 0, u will equal 1. Let's do that's an implied. X equals to 2 tells us that u is going to equal to 5. So if we call this like I for integral or something, so sticking that all together, our limits now are going to be from 1 to 5. X on the top has been replaced with u minus 1 over 2. And on the bottom, the 2x plus 1 is now u, and that is all cubed. Dx is 2 dx. So we can cancel off that 2 with the half in there. What we're left with then, integral from 1 to 5, u minus 1 over u cubed. So this is much nicer. It feels like, oh, is that any different? Yeah. The cube, the high power now, is on just like a single thing. It's not on a binomial. That's much nicer because we're able to go through, and every term on the top, we can just divide it off individually. So u over u cubed is u to the minus 2. And 1 over u cubed is u to the minus 3. Again, still the limits of 5 and 1. Doing these though, so minus 2 raises to minus 1. Divide by that minus 1. Minus 3 raises to minus 2. Divide by that minus 2. So half at the front. And then we'll plug in 5 and 1. So plug in the 5. What are we going to have? I'm going to do it. See, it's now negative and positive. So I'm going to write this one, take away this one. I think it's easier to do. So this is a half of 1 over 5 squared. So 1 over 25. Take away 1 over 5. And then all of that stuff, we're going to take away a half, take away 1. So a half. No, sorry. Yeah, a half take away 1. So negative a half. Doing this then, we've got 1/50th, and that's 1 over 5. Let's just change that 1 over 5 to 10/50ths. So this is going to be 1/50th, take away 10/50th is negative 9 over 50. Plus a half, which is 25 over 50. So altogether I get 16 over 50. Cancel that off, 8 over 25. Again, it looks quite nice. Numbers like 8 and 25, square cube numbers seem okay. I will again double check that this is fine, just to make sure that everything's all right. In the exam, how can you check? It's not really such a nice way to check. It's just making sure you've made no mistakes with like calculator stuff. Do you know what I mean? But we will see if this gives us the right answer. Negative 1 over 5th. Yeah, that looks fine. 1 over 1. This would be a half, wouldn't it? This would be. Yeah, that looks fine. Is that definitely okay? Half that. Yeah, it all looks fine. So yeah, I will check on the calculator, make sure it's all okay. Like I say, if you don't hit anything else, then everything's gonna be good. And I'd always, when I'm doing this on the calculator, how I'm checking it is I'm doing the original one. I'm not going to check like the substituted, the version after I've substituted it, whatever that would, however you say that. Always doing the original one, just in case my substitution was wrong beforehand. This gives me 0.08. Let's pick 25. Oh, that's not quite right. I'm a factor of 4 off. Should this? Yeah, okay. I'm a factor of 4 off. Let's see what I've done wrong. Is here du is 2 dx. But what I've done is I've replaced dx with, firstly I've written dx, but I've replaced it, I've done it the wrong way around, does that make sense? So this should not have cancelled off. Let's trace through what should have happened. Is that this 2, like a 2 down here, shouldn't have cancelled out with that one, because it shouldn't have been a 2. It should have been a half, and that dx should have been a du. So effectively, all that's going to change going through, where this half did cancel with like the 2 that was here, instead they're going to combine to make a quarter. So we have a quarter going out the front, and that quarter tracks us all the way through. And then at the very end, we would just have a quarter of all of this stuff. So a quarter of 8 is 2. We get 2 over 25, and that is 0.08. See, it's very easy to get slipped off up. This is something to be careful of. There's no way to stop you ever making these little mistakes completely. They will slip in there. It's going to happen. Just about when you're revising, what common mistakes do you make like that? Like you might get your I's and J's mixed up, stuff like that. Do you know what I mean? You might do something like that. I've just written this the wrong way around. Just be aware of the ones you make. You're not going to stop yourself making all of them. But then in the exam, if this is something you do quite common, then you want to go and just, when you do this step, just take extra care. Make sure you've got the right way around. Or find a kind of workaround. Can you avoid that step completely? Like I used to really struggle with doing say minus x is greater than 6, and then for some reason times it by the negative and then flipping the sign. I didn't like it. Don't know why. But I just learned to just always add x and take 6. So avoiding the step that I got confused by, just so I didn't have to do it basically. Finding workarounds, finding solutions that stop you from making mistakes that you're going to keep you slipping up on naturally. That looks good though. We do need to check the answer. I could have checked it earlier on, can I? That would have been a bit easier. Let's keep going though. Number 14. What's that saying? Show that this stuff is all true. So on here, it looks like it's r cos theta plus alpha, but it's not. It's like the reverse of that. I mean, here we've got 2 of these ones and one single one. You could kind of think that way around, but it's like if you just do the substitution. But most likely, what we're going to do is use the double angle formulas. So we're going to have sine of x cos of 30 plus cos of x sine of 30, and then plus root 3 lots of cos. So that's going to be cos x cos 30. Take away root 3 lots of sine x sine 30. Let's get some of these numbers then. So all the stuff with the 30s, we can work out what they are. So all the sine, cos 30s is root 3 on 2. So this is going to be root 3 on 2 sine x. And all the sine 30s are a half. It's half of cos x. This again is root 3 on 2. Times the root 3's together, you get a 3. So it's 3 on 2. Lots of cos x. And at the end, again, this is going to be a half. So it's take away root 3 on 2, lots of sine x. If we look at that first and last term, then the sine x's, we have root 3 on 2 of both of them. So they can cancel out because one's positive, one's negative. And in the middle, I've got half a cos. I've got 1.5 coses. So altogether, I have 2 coses. And that's what they wanted. So that's always a good sign. Part B then, solve this thing. So this is the same as this, but x is now theta. So we're going to swap this thing out for this thing out and then solve it. So we'll have 2 cos theta equals to 3 sine of 2 theta. And these have different multiples of theta, so I'm going to take the double and expand that out. So that right hand side is now going to be 6 sine theta cos theta. This is good. Don't cancel the cos. Factorize the cos. That's going to go to the left a little bit. Yeah, factorize the cos. So if we bring the cos to the other side, what we're going to have is cos theta lots of 6 sine theta minus 2. So taking the 2 cos over the other side, we'd have a negative on this side, and then just factorizing that out. That would all equal 0. What does that tell us? That we have 2 ways to get solutions, either that cos theta is equal to 0, or that sine theta is a third. That's good. Let's just draw this out, see what's going on. So we've got our x and our y. We've got our sine doing things. How far do we draw actually? Only to 180. Okay, so less bits to draw. Our sine's doing stuff, and our cos is doing stuff as well. We want answers when cos is 0, and when sine is equal to a third. That's there-ish, isn't it? Ish. Don't know exactly, but it's going to be symmetrical. So let's look. Inverse of cos at 0 is equal to 90, but I'm going to guess we need, nope, we do need degrees here, 90. And if we look at the inverse of sine at 0, what does that, oh, not at 0, sorry, at 1/3, that gives us, I want it in degrees, 19.5. What decimals? One decimal place, yeah, 19.5. So that's good. That's the principal value. Then we use the symmetry. So you can see like this here is 19.5. So this being 180 over there, the gap size is the same. Do you know what I mean? It's all symmetrical. So this is going to be 160.5. And this middle one is just the 90 degrees. So we have those three answers. Theta will be 19.5, 90, or 160.5. That looks good. That's 14 done. Let's keep going. Got some sector stuff. So design of a stage. Yeah, we've got a sector joined by a little rectangle. We've got some lengths. So the radius of the sector is r. That's r. That's r. That's theta in the angle. The length and the width are r and a tenth of r. R and 10. R and 10. Total area is 240. Find the perimeter. Okay. So let's work out like the stuff for the area then. So the area here of the rectangle is going to be a tenth of r times r. So r squared on 10. Plus the area of the sector, which is always going to be r squared theta on 2. And this then, was it 480? 240. So it's equal to 240. Why I've done that first is effectively, if you look down here in the perimeter, there's no theta. The angle isn't part of that. How they've got rid of that is by using this equation. So using the fact they give you, the value they give you, to rearrange that for theta, and then we're able to sub that into the equation for the perimeter instead of where we would put the thetas. So let's do this. First thing I'm going to do is factorize like r squared over 2 out of everything, I think. Or, yeah, I think I will do that. So r squared over 2, lots of, it's going to be a fifth plus theta. So that's equal to 240 still. I'm going to double it, 480, divide by the r squared, and take away a fifth. And that should be our theta. What does that look like down here for the answer? It doesn't look too bad actually. I'm wondering like, is it worth making this into like that's r squared, this is 5 times this by 5? No. Like making it into one fraction. Down here it's in two different parts with a 480 on. So I probably want to leave that as 480, not like 5 times 480, whatever that number would be. So this is good. Let's think perimeter wise now then. What do we get for the perimeter here? Well, we've got this is r. And then the next one is a tenth of r. And then we get another r on the bottom. Then another tenth of r. And then we have the arc all the way around. So that is going to be our theta. So did I get, I got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's good. So let's combine these together. How many r's do I have there? Well, I have 1, 2, 2.1, 2.2. So 2.2 is 11 over 5 and a theta. Oh, I'm putting a theta. Yeah, I'll put a theta there for now and then we'll put that in the next line. That's all times by r. Let's plug in those values then. So 11 over 5 is 11 over 5. But theta, that is 480 over the r squared, and we'll take away that fifth. So again, this fifth has been quite nice actually, because you can see that we'll just make the 11 fifths and the 1/5 make 2. So I've got 2 in the brackets. I'll expand the brackets as well. So 2 times r, and then the 480 is over the r. And that is hopefully what they were after. Yeah, lovely. 2r, 480 over r. Lovely jubbly. So now we need to differentiate. Find the value of r for which p has a stationary value. So I think this 480 r to the minus 1 is where you can rewrite it. So dp dr, 2r will become 2. The 480 r to the minus 1, well, the minus 1 will give us a negative at the front. 480 will stay, but it will be r to the minus 2. Probably re-rough writing that just as it's 2 minus, wrong place, equals 2 minus 480 over r squared. Just in case you need to use it, it's not bad to have it there. Yeah, we need to use it, don't we? Equal to 0. So effectively, we want the 480 over r squared equal to 2. So the r squared needs to be 960. So r is the square root of 960, which is 8 root 15. The root doesn't look too nice, but it's not the end of the world. Yeah, it doesn't look like the end of the world there. Something I'm not trusting, I don't know why. Sometimes you get a feeling of like something's going to be wrong, but I will double check at the end to see if everything's fine. This is 2. It was minus 1 there, and so it does stay as minus 1. That's whoops. Yeah, it needs to be 960, doesn't it? Yeah, that looks fine. Lovely, that looks good. We will have a look at part C. So prove it is a minimum. So to do that, we want to find the second derivative. So d2p dr squared. So differentiating this thing. So the 2 will go. The r, well, r to the minus 2. Minus 2 comes to the front, so we'll have positive 960. R to the minus 3. So this is going to be like, if it's positive r, it's positive, negative r is negative. But if we plug in the value, so plugging in r as 8 root 15, it's going to give us some number. Don't know what number it is. So 960 times by that thing cubed, or minus 3. I get it's not, yeah, it's some horrible number. 0.03227. I don't want that second decimal in there. Something like that. Doesn't matter exactly what it is. What matters is it is positive. So therefore, that is a minimum value. That's what we need to do. Yeah, show that this second derivative is positive when we plug in our value for r. Lovely jubbly. Let's keep going then. Do we have any more on here? Yeah, number 16. So we've got something here. We want to integrate it, don't we? Is that the whole thing, really? Use a substitution. And then find, yeah. So if we just found the whole thing, we'd get all the marks. So let's do that. We will do the substitution they want us to do, though. So this is 1 and root 3. X is going to be 2 sine u. So firstly then, let's make x equal to the 1. So sine u would be a half. So u is whatever the inverse of a half is going to be. Does it have a nice inverse? I don't think it does. Yeah, it does, doesn't it? Yeah, inverse of a half is pi 6. And if we make x equal to root 3, then sine u is going to be root 3 on 2. So u will be pi 6. No, pi 3, sorry. This is 30 degrees and 60 degrees. That's good. Look at this bit then. We need to do dx du. That would be 2 cos u. So dx is 2 cos u du. Where I made that mistake earlier, I will be very careful to make sure I get this all the correct way around. That looks good though. Let's fill all the bits in. So did I call it r? Yeah, r should be the integral from pi on 3 to pi on 6. Nope, other way around. Pi on 6 to pi on 3. Is it? Yeah, one on the bottom. Of 1 on the top. That's good. I'll actually put my dx up the top. So dx was 2 cos u du. And on the bottom then, x squared will be 2 sine, well, 4 sine squared u. And then 4 minus 4 sine squared u. This looks good. Was that squared, that thing at the bottom? No, it was square rooted though, so we'll write as a half. That's good. Inside this bracket, it's like they've done this for a reason. This is something that's quite common. This is 4 cos squared u. So when we square root it, it's just 2 cos u. So that square root bracket on the bottom cancels out with the 2 cos u on the top. What we're left with then is the integral with our limits of pi on 3 and pi on 6 of, we've got that 4 on the bottom down there. I'll take that out, so it's a quarter out the front. And then we can see we have a sine squared, and that's it. The du is still there, obviously, but yeah, just sine squared. That's on the bottom though, so that is cosec squared of u. So we can see here, yeah, k is going to be a quarter in this case. This is good. Actually, solving this now then. The integral of cosec is in the formula book. Do I remember it? I think I do. Is it cot? I think it's cot. So therefore r is equal to, we want to do cot of u, got a quarter of that, evaluated at pi on 3 and pi on 6. So plugging all these bits in there, if we think about it, it is going to be a quarter of 1 on tan of 60 degrees, which is pi on 3. Take away 1 on tan of 30 degrees, which is 1 on 6, or pi on 6. So tan of 30 is 1 on root 3. So 1 over that is actually root 3. And this one, is that the wrong way around? Yeah, wrong way around, sorry. So the first one is going to be 1 over root 3. And the second one is 1 over root 3. So root 3. And then we have a quarter of, this is effectively root 3 on root 3. So it's a third of root 3. But we're going to take away, I think I've faffed this up. Let's start that little bit again. Go back to that bit. Cot of pi on 3. So 1 over tan of pi on 3 is 60 degrees. Gives us root 3 on root 3. Root 3 on 3. If I do the same thing for 30 degrees, I get root 3. And then I have a quarter of that. Should it be negative? Shouldn't be negative, is the concern I have. How about I just put these all in the wrong way around? That's what I'm wondering. It's a third. So root 3 on 3. Take away root 3, divided by 4. Negative root 3 on 6. Should it be negative? It should not. So something's gone awry. I've got a feeling that where I've done the integral of cosec squared, that's actually negative. So all of this should have just been a negative what we have. I will double check that very quickly, just to see if we're all good. So integrate cosec. Do we get negative, sorry, cosec squared? Pretty sure we do. Yep, negative cot. So yeah, that's all good. That's all spot on. Everything matches up. Again, I will double check on the calculator later on to see if this is the correct answer, but nothing looks awry there. Do you know what I mean? Like the number doesn't seem horrendous for what we've been doing. Do we have any more? Nope, that's the last one. Lovely. I'll double check everything. If it's all fine, this will be the end of the video. If not, there will be corrections at the end. Do you know what I mean? Anything else that looks wrong, give me a shout. If not, I will see you in the next one. Lovely. Thank you very much. One little mistake just on this. What question was this? 15. That was at a half. Yeah, this shouldn't go up. It shouldn't double from 480 to 960. It should half down to 240. So that's a quarter of what it was. So when you square that, it's a half what it should have been. So it should go down to 4 root 15 instead. Did we use that later on? Yeah, it got used in here. This should have been a different number. This should have been 4. So was the differentiation fine? Differentiation was fine, didn't it? Yeah, because it's then just solving it later on. That's the problem. So yeah, different number than what goes into there. Let's double check that's fine. So 960 over this, well, square root of 240 all cubed gives us still a small number, it's like 0.25-ish, 2581, or 82, blah, blah, blah. But either way, it's still positive. Same result from the question, doesn't change what we actually did at the end. Yeah, no difference in this part of it. But yeah, just that number. I doubled instead of halved. So we should have like had half the answer basically at the end. That all looks good to me. Thank you very much. I will see you next time.